Greetings everyone and welcome back to another exciting lecture in geomorphology. We're going to be continuing along today with our discussion of weathering. And so in our last video series, we were thinking a lot about physical weathering, right? We were thinking about physical weathering processes such as freeze-thaw and repeated freeze-thaw cycles that will break apart rocks. We were talking about salt weathering. We were talking about exfoliation. Well, today we're going to move on and we're going to talk about chemical weathering. And you already learned a little bit about chemical weathering in our last lecture when I showed you a picture of this, right? You all remember this? This was our granite rock that looked like it had two different parts to it. We saw this fresh granite here that had fresh colors and was really resistant. Here it was really hard. And then we had this more weathered granite down here that was red in color, right? That red in color down here. And remember, I said, hey, if you took a knife and tried to stick the knife into the granite, the fresh granite up here, it would just get stuck in there, right? And you couldn't really hit it in at all. You'd break the tip off your rock. But down here, if we were down in this reddish material down here, if I stuck my knife in, I'd be able to stick it all the way in. Look at that. Look how far I can stick this knife into that weathered rock up here. It gets stuck right there. I can't do it. The difference is we've seen deep chemical weathering here in the formation of a saprolite. So saprolite is when we've had intensive chemical weathering of the rock, but we actually haven't had a volume change within the rock yet. So that's remember what chemical weathering is. So again, those distinctions between physical and chemical weathering. In physical weathering, all we're doing is taking a big rock and turning it into smaller and smaller pieces of rock. Chemical weathering is very different. In chemical weathering, we're talking about decomposition. We're talking about taking the primary minerals within a rock and doing chemical reactions to them to forming new minerals that are more stable at the Earth's surface. And remember, we talked about a very important set of secondary minerals like clay minerals that are more stable at the Earth's surface, and that's often what we see. Let's take a step back. Before we get to the weathering products, let's talk about something more foundational in chemical weathering. And that's thinking about when we have our primary minerals, how are they going to, how susceptible to weathering are they going to be? We've talked a little bit about this, right? We've already talked about how different rocks will have different susceptibilities to weathering in general. But if we think about chemical weathering in particular, what we see is that different minerals have different susceptibility to weathering. So some minerals will weather more easily at the Earth's surface and other minerals will not. And we can understand that actually by thinking all the way back to our introductory geology class when you learned about the formation of rocks from a magma. So does everyone remember back to Bowen's reaction series? So here's Bowen's reaction series up here, and we're looking at kind of minerals here, right? We're talking about different minerals that are in igneous rocks, from olivines to pyroxenes to amphiboles to biotites to feldspars, muscovites, and quartz, right? These are all different types of minerals that you find in igneous rocks. And what you learn from Bowen's reaction series is that as you take a melt and you start to crystallize that melt, the minerals will precipitate out and form crystals at different temperatures. So the first to crystallize out at the highest temperature are going to be your olivines and your pyroxenes, and those are going to form ultramafic rocks. As we move down to slightly cooler temperatures, the next to crystallize out are going to be lots of those pyroxenes and amphiboles, and we start to get more basaltic rocks and as we move towards the quartz end of things, we start to see the feldspars and muscovites precipitating out, and we form granitic rocks. And so that's Bowen's reaction series, right? Well, interestingly, that stability we use for understanding which minerals are going to crystallize out of a melt, we flip that, and that's going to be our Goldrich's weathering series. It's kind of the opposite. So that's what's shown over here. We see that the minerals that form at the highest temperatures, the olivines and the pyroxenes, are going to be the first to weather at the Earth's surface. They're going to be the least stable. And then what we end up with all the way down here, the most stable, is quartz. And intuitively, this kind of already makes sense to you, right? When you go out to a beach, picture your favorite beach. You're sitting on that beach, having a soda, reading a novel. What color is the beach sand? Now, I bet for most of you, you said that it was probably tannish in color, right? White to tan in color. And that's because if we think about weathering over the Earth's surface, we bring all the rocks up in the mountains and we weather them as we transport out those rocks through the fluvial system and dump them on beaches. We will preferentially weather out the olivines and the pyroxenes, and we're going to be left with just those feldspars and quartzes. And that's why beaches are often light in color, because most of your beach sand is quartz and feldspar, those most stable minerals that are least susceptible to weathering. And I know one of you is saying, Lyman, you're totally wrong. I was imagining being on a green beach. And that's true. You definitely have certain locations where you can have green beaches, where the dominant material on the beach is probably olivine. And that would happen in places like Hawaii, where you have a bunch of mafic rocks. And so, yes, that can happen, but most cases, that's not what's happening. Okay, when we think about chemical weathering, another thing that's going to be really, really important is this right here. We need precipitation. We need water to drive these chemical reactions. And so that's why tropical climates are where we see lots and lots amounts of chemical weathering relative to physical weathering, because we need that water to drive those chemical reactions. So generally in deserts, we see less chemical weathering where it's dry. When we think about chemical weathering, we kind of break it into two phases. The first stage is what we call geochemical weathering. And geochemical weathering is where we just essentially take the bedrock and we weather that bedrock through chemical weathering processes. And so that happens kind of at the outcrop. And we can make things like saprolite that you guys have been learning about. The second stage of chemical weathering is what we call pedochemical weathering. And that's the weathering of unconsolidated materials in the formation of soils. So here's a spectacular soil profile right here. We've got these different layers here. We'll learn about soils soon. And we see chemical weathering that happens within these horizons that give these different layers their distinct characteristics. So we'll be talking about that soon. But we're going to stick with thinking about kind of that geochemical weathering for a lot of today. Okay, when talking about chemical weathering, one of the most important differences we think about is your weathering going to be congruent or incongruent? And so congruent weathering is where we have the complete transfer of the minerals themselves out of the system. Does that make sense? So we kind of chemically weather the mineral. It doesn't form a secondary mineral, and you just flush it out in water as ions in the water, and it's removed. Congruent weathering you really only find in certain locations. And where we find congruent weathering is where we can have rocks like this. So this is the Burren and Ireland, and a rock that we can do congruent weathering would be limestone, calcium carbonate. And so we can easily do that in limestone. Okay, so another term I need to introduce here that we've talked a little bit about is solution. And so when we're talking about solution here, we're talking about essentially that transfer of mass from the solid to the aqueous phase. So we've dissolved away our limestone. We're making a solution that has the elements that were in that solid phase. So here, the solution reaction we're talking about is calcium carbonate. Hold on, this video started playing and I didn't want it to yet. I'll start that up again in a second here. So in this case, a chemical reaction that you did in your intro lab, right? You did the test to see if a rock has calcium carbonate in it. How did you do that? You used HCl, hydrochloric acid. And so when we have this chemical reaction, this is a chemical weathering, we're taking our calcium carbonate, we are adding hydrochloric acid to it, and what are we making? We're making an aqueous calcium chloride solution, we're making CO2 gas, and we're making water. Notice here that nothing is in the solid phase. Nothing at all here is in the solid phase. And so that is really important for chemical weathering. Okay, so moving on. Sorry, I'm putting the audio levels. Looks like they were peaking a little bit. Maybe not now. Okay, anyway, moving on. Yeah, right? Does everyone see that here? That we have aqueous, we have a gas, and we have liquid, but we don't have any solid product. So this would be a congruent reaction. If I go back to this video here, get rid of the ads, we can see the dropping of hydrochloric acid onto the limestone and see that fizzing, right? That fizzing, that's the reaction, and that's the off-gassing of carbon dioxide. And then we still have a solution that has the water and the calcium chloride solution. So that would be a great example of a congruent chemical weathering reaction. We really only see congruent weathering in locations where we have limestone. So here's the burn again. And so this surface has been completely scraped, actually cleaned by glaciers. That's actually what's made this nice flat surface. But then, does everyone see these deep grooves? This is where we are getting water. We get rainwater that gets into fractures in the limestone, and it's dissolving it away. And we're really getting nothing else that's forming. And that's why you see very, very little vegetation across the landscape like the Burren, because it's hard to make a soil when all your weathered material is just getting flushed out of the system. So a zoom in here, here's a zoom in. You can really get to see what these cracks look like. This is Paul in the background here, who's showing off the jumping over the big fractures here and the dissolving away of the limestone. Again, so you have very, very thin soils in the Burren, and you can make great rock walls out of the weathered limestone blocks as well. That's an impressive wall, isn't it? Okay, and here's some dissolution pits right in the limestone surface as well. So if we zoom in a little bit here, does everyone see this? This is a really cool positive feedback loop that we get, and we form these dissolution pits, right? Because when it rains, you get water that's going to collect in the pit, and so it dissolves, and you get more water in that pit, and so it's positive feedback, and you end up creating a larger and larger pit. So those are dissolution pits. We can see some other really cool dissolution features here in the limestone. And just for fun, where we're going in the semester, does everyone see these giant boulders here? Those are glacial erratics that were deposited as this limestone surface was scraped flat, and we dumped these big boulders off. Okay, so that's congruent weathering. Moving on from this kind of brown color, and it's often associated with fractures in the rock. That's essentially those secondary minerals that are forming. And so that happens when we have incongruent weathering, where some of the material is transferred into solution, but other are incorporated into new minerals that are created at the weathering site. So that would be incongruent weathering. Okay, let's talk about some processes now that form chemical weather, that drive chemical weathering. So the first one I want to talk about are oxidation and reduction reactions. And these involve the transfer of electrons from one element to another that's going to result in a change in charge to the electron, and it's going to actually drive some chemical reactions that we see at the Earth's surface. So an oxidation reaction, so here's an oxidation reaction where we have an electron donor that donates the electron, and then we have an electron acceptor, and so that would be an oxidation reaction, and then we end up with an oxidized donor that doesn't have that oxide, and then the reduction reaction is when we actually gain an electron, and so that ends up being a reduced acceptor there. So oxidation reduction reactions. So again, a nice way to think about it: in oxidation, you're losing electrons. In reduction reactions, you're gaining electrons. And you've seen some very common oxidation reactions in nature. Oxidation is really common at the Earth's surface because we have an abundance of oxygen. That's why your car rusts here, as we're driving oxidation reactions in the steel of your car. when we start thinking about oxidation reduction reactions, a term we're going to want to use is the redox potential, EH, which tells us how much free oxygen we have in the system. And so EH is going to really depend on how much dissolved organic matter is in your solution. Generally, our EH is high enough to oxidize most elements. And so that's all I'm really going to say about this right now. But what oxidation ends up doing is creating basically the formation of minerals at the Earth's surface that generally have kind of a red, black, or yellow coating. And those are generally iron oxides or manganese oxides that have formed during weathering reactions. So when we oxidize a mineral, we generally form some sort of hydroxide. This is a type of mineral class. And these are, once we form them, they're insoluble, meaning that we can't redissolve them into a solution, and they're hard to move. And so that's, you often see like staining, that red staining in soils, because when we make these oxidized elements, it's really hard to move them again. Okay. Thinking on the other end, when we have reduction reactions and we end up with reduced elements, these are far more mobile and our electrons can go back and forth. Okay, so this oxidation process makes a lot of red colors that we see in landscapes. And so oftentimes an oxidation reaction will produce hematite. Whoops. There we go, hematite. And then in hematite, which is an iron oxide, we end up with that red color. Those oxidation reactions often make those kind of red and yellow colors. And so we can see the chemical weathering here in this class. And look at that. Remember, we've talked about weathering lines. We're more red, orange because of those oxidized minerals, those secondary minerals that are accumulating in the class. So that would be a classic oxidation reaction. Okay, the opposite of that would be a reducing reaction, and where we generally see reducing environments are oxygen poor environments. So generally like underwater would be a great place. So here's a hunk of soil right here. This is that I dug out of a soil pit in Yellowstone National Park. And do you see right about here we go, this was at the water line. So everything here in these green colors, those, let's zoom in. Right here, these green colors, that was below the water table in a reducing environment. And we have iron in its reduced state, which gives us that really cool blue-green color. We call these Gallade colors. And then above it, up top here, we were above the water table and we had oxidation, and we get those red colors. Okay, so that's oxidation versus reductions. Okay, and we're back. Sorry about that. We've been talking about these oxidation reduction reactions and how important they are in chemical weathering that we find at the Earth's surface. I want to talk a little bit more about chemical weathering, and moving on, I want to talk about another really important control on chemical weathering and chemical weathering environments, and that's pH. And so when we have pore water that's moving either through soils or through bedrock, the pH of that water is going to be really important, as it's going to determine what types of chemical reactions we have. And so when we think about kind of most water at the Earth's surface, it's generally fairly acidic, 5.7. And that's mostly due to carbonic acid. And that's rainfall's acidic because we have rain that's falling through the atmosphere. And as it does, it's mixing with carbon dioxide and becomes slightly acidic as you form carbonic acid. We also see carbon dioxide in soils as well. And so we have carbonic acid that forms in soils. And so because of that, we end up with slightly acidic. Remember, 7 is neutral on the pH scale. Anything less than that is acidic, and the lower the number, the more acidic it is, right? So here's your standard normal water, 5.7. Acid rain would be less than 5.6. We see non-calcic soils are generally an acidic environment at about 4.6, and then vinegar or Coca-Cola are much, much more acidic. And so the reason that pH and acidity is so important in chemical weathering is the solubility of minerals changes depending on the pH. So solubility, how likely it is for that mineral to go from the solid into the aqueous, depends on pH. For example, have a look at the solubility here of silica, SiO2. So essentially we're thinking about quartz here. And sorry, let's fix that real quick. Our graph is off on the side a little bit, our axis. I don't know how that happened. Let's go back. There we go. Now we're back. If we look at the pH scale on the x-axis here, and sorry, I've got to move it so I can see it myself too. There we go. Okay, if we see this, pH values here, we're looking at the solubility. That's our y-axis, solubility, where low numbers here mean that you really can't dissolve that material. It's going to stay in the solid form. High solubility means you can dissolve that. And so look how dependent this is on the pH of the solution. And so here, if we have kind of neutral or acidic environments, silica is very stable. So that means that silicate minerals, quartz and feldspar, are going to be very, very stable at the Earth's surface, right? Much more so than a mineral that's not nearly as insoluble at these low pHs, right? So that's why, again, quartz and feldspar are what you find on beaches, because generally we have slightly acidic conditions at the Earth's surface, and quartz is very, very stable in those conditions. Okay, look at the difference though with, say, another common mineral we see, calcium carbonate. And so calcium carbonate, we see an abrupt transition to where calcium carbonate is highly, highly soluble versus insoluble. And so this is why when you drop a little hydrochloric acid on your seashell or on your limestone rock, it fizzes so much, because you have very, very high solubility at low acidic pHs. And then as we move to more basic environments, we have basically it's impossible to dissolve that calcium carbonate. Another really important mineral are things like aluminum oxides, right? So aluminum oxides here, weathering products, we generally see that these are insoluble at normal pHs, but highly, highly soluble in both basic and acidic solutions. And so that's really important for things like acid mine drainage. And so why is that? Well, a lot of these these aluminum oxides, they precipitate, aluminum and iron oxides, they precipitate out of mine waters. And so here we've got an example of this, yellow boy, which is this kind of nasty yellow-orange material. Does everyone see that here? And this stuff often is associated with mine wastes. And what happens is that in the mine itself, you have very, very acidic water, and so you dissolve the iron and the aluminum. You dissolve the metals, and then as you exit the mine, you precipitate out these really, really nasty metals, iron oxides and aluminum oxides, and so that can smother vegetation, and that's a really big negative impact associated with mining. Is that acidic water that allows you to mobilize these aluminum oxides, iron oxides, and then they precipitate out. They're insoluble in more neutral environments, so they're kind of hard to get rid of. Okay, so moving on, another really important chemical weathering process are hydrolysis reactions. And hydrolysis reactions are where we have a water molecule and we split that water molecule into hydrogen and oxygen, and those can actually go and weather and break apart and drive chemical reactions in minerals. And these are particularly important. Hydrolysis reactions are really, really, really important in silicate minerals. Silicate minerals are quite susceptible to hydrolysis reactions, and that's big, right? That's really important because most of the Earth's crust is made up of silicate minerals. So the example here that we're looking at is we have a silicate mineral here in a solid form. We're going to add water to it. We're adding water to it. We're going to mix in a little carbonate here, and what we're going to drive is we're going to create a clay mineral and some ions in solution and some silicic acid. So in this case here, we've got our mineral, our feldspar mineral. In this case, it's plagioclase. We're mixing in some water, mixing in a little bit of that carbonic acid, and we're going to precipitate out our stable secondary mineral, and that is kaolinite, plus a sodium ion in solution, and then we're going to get a bicarbonate ion as well, and silicic acid. And so these hydrolysis reactions are really important for weathering at the Earth's surface. Okay, let's talk a little bit more about some really cool morphologies associated with chemical weathering. We'll often see quartz relief in bedrock exposures because quartz is the least weatherable material. So if you have a layered rock of quartz and a mica, what happens is you're going to have more chemical weathering in the mica and the quartz is going to stick out. And so we call this quartz relief. Okay. Moving on, remember we've got the primary minerals, which are the original components of the rock. And then we got those secondary minerals. And the secondary minerals are created in the weathering zone. They're more stable because they reach equilibrium with the conditions at the surface of the Earth. And so they're stable. Generally, what we end up with for secondary minerals are either clay minerals or hydrous oxides, so iron oxides or aluminum oxides. Those are generally what we see at the Earth's surface. Okay. So let's look at a little bit about the structure of one of these secondary minerals, clay minerals. It's actually really important because it gives it that property of being able to shrink and swell. So clay minerals are layered minerals. And so if we look at the actual structure of a clay mineral, it's composed of two things: a sheet of silica tetrahedrons, these SiO4s over here, and then a sheet of aluminum octahedra over here. So we have one aluminum and our hold on, I'm getting an audio issue again. Okay, we're back again looking at those silica tetrahedra and aluminum octahedra over here. And so the aluminum octahedra are composed of one aluminum atom and 6 oxygen atoms. And we end up basically mixing these layers. So we have layers here of aluminum octahedras and silicon tetrahedras. And we have generally what we call two structures for our clay minerals. We can have 2-1 structure, which is shown right here. Let me circle it here. Okay, so 2-1 structure. In a 2-1 structure, we have 2 layers of the silica tetrahedra and then 1 layer of the aluminum octahedra, versus a 1-1 structure. And so in 1-1 structure, it's 1-to-1. So we get 1 aluminum octahedra sheet and then 1 silicon tetrahedron sheet. And so those, essentially the ordering and the numbers of those sheets determine what types of clay minerals we have. And this is really, really important because it's going to essentially determine how much our clays can expand. And I talked about clay and shrink swell being really, really important in physical weathering. Well, it's the chemical, it's basically the type of clay you have that can have lots and lots of shrink swelling ability. And so we've got an example here, first off, of an illite, which is a non-expandable clay. We've got, it's a 2-1, but those sheets are kind of connected together. And so they've got a potassium ion in between them. And so those layers are pretty well locked together. However, Vermiculite, which is another 2-1 clay, we can actually put a ton of water into the in between the layers of the sheets of the silica tetrahedra of an aluminum octahedra, and so they can swell as you add more and more water in. And then another example, smectite would be another clay that you can add even more water into. So smectite is, you can really expand it when you have water. And then another example of a 1-1 clay here, this is kaolinite, and kaolinite generally is non-expandable, that your layers are kind of bonded together. So this is really important when we look at things like this. So here's some mud cracks. And so mud cracks, when you wet them, you swell those clays up, and then when you dry them, they contract and you crack. So mud cracking is caused by the shrink swellability of clays like smectites. Okay, and then as I mentioned as well, the spectacular landscapes of the Badlands, where you have that popcorn texture, is associated with shrink swell in the clays in the bedrock. Okay, our final slide is just looking at areas where we have bedrock with lots of clay in them, where we have these shrink swells. So places like Texas, and also up in the Badlands area here in the Dakotas are areas with lots and lots of these clays. Okay, that's all we've got for you on chemical weathering. We'll meet in class to talk a little bit more about it. Thanks for listening.